Okay, great. Okay, folks, so welcome to, I guess we're in week 6, week 5. The group keeps getting smaller. I think we're down to 12 people now in total who are officially still in and still contributing, which is good. It's about the number I expected, so let me think about logistical updates. So you had a problem set due, and Gabe will talk to you about that after lecture, where you looked at SO31 and the Lorentz transformations, and you looked at some angular momentum identities, which I don't remember what I put on there, but depending on what I put on there, some might have been more fun than others. And you looked at the Poincare group, which for those, I won't spoil the fun because Gabe will tell you what the differences are. And in a quantum field theory class, you probably spend 2 or 3 lectures going over all the symmetries of the Lorentz group and working out all the algebra of the Lorentz group, which is something we'll do next term. What else? Right, there's no problem set this week, which is good, because I want you guys to have time to think about your papers and not have to worry about doing some problems. So next week, there's no problem solving session. Instead, I'll be here after lecture for those of you that want to discuss your papers. So that will sort of take the place of the problem solving session, give Gabe a break too for a week. And this way we can all discuss. And you'll have no problem set the week after either. And I'll do a similar thing after lecture the week after. If you guys want to discuss the papers you're about to turn in, I'll be here to do that. Okay, a lot of you have been asking me about topics and things, which is good. We can keep discussing and you guys can figure things out and it should all be good. Okay, any questions from last week or about the homework or about the research paper or anything before we start today? Okay, let's jump right in. So we have been looking at, we sort of have all the tools now to do calculations in quantum mechanics. We know about state vectors. We know our Brockett notation. We know about continuous wave functions. We know how quantum mechanical principles apply to our study of the natural world. Now the question is, well, what can we compute? That's very important. What kinds of things can we compute? What kinds of numbers can we get? So today I'm going to sort of start on doing some practical computations. What I will say is the simplest examples in quantum mechanics are kind of contrived. So they're not real examples you'll find in the lab, but they're good examples to sort of test the waters in doing some computations, which is what we're going to do today. So what are we going to do today? We're going to derive the not really derive it. I'm sort of going to posit it, and you can interpret why it is the way it is. But we are going to derive the Schrödinger equation, quote unquote, the time-independent Schrödinger equation in 3 dimensions and in 1 dimension. And then we're going to solve some systems, just like you did in AP physics or in high school physics. We're going to solve some systems this week and next week. So next week, we're going to do the harmonic oscillator, and we're going to do the hydrogen atom, which involves a bit more machinery. And this week, we're going to do some simpler ones, the particle in the box, or the infinite square well, which I'll describe to you, and the free particle. And we're going to compute some dynamical quantities. So let's get right into it. One thing I will say is now you're going to start to see why having a good foundation in mechanics and other physics is so important, because it really is all connected. I mean, you can get away with not knowing classical mechanics or electricity, magnetism, and all that stuff, but eventually you're going to have to teach the foundations to yourself. It's very, very important in physics to have a good foundation, right? You can't sort of jump rings on the ladder. So I encourage you, if I describe to you something and I use a classical analog, go read about it in your free time, right? Go do it, go understand the classical dynamics of the system. It's very important. And every physicist can do any classical system because you have to be able to understand them. Okay, great. But before we jump into the Schrödinger equation, I want to talk about a special class of equations called differential equations. The reason I want to talk about them is because the Schrödinger equation is a differential equation. It's a type of differential equation. Some of you may have heard this term, differential equation. It's usually talked about as this big term, and you'll take a whole class on differential equations. I did not, by the way, sort of skipped it. It's not mandatory. Because in physics, you can sort of learn the differential equations as you go. You don't really need to take a whole course on it, although it obviously helps. So you guys have all seen a differential equation already. You don't even know it. That's F equals ma. So why is F equals ma a differential equation? Let's think about this. So F equals ma. We'll go back to just the first equation you learn in high school physics. Why is this a differential equation? Let's look at the A. So I'm going to use physicist notation now. So X is position, okay? Okay, X is position. X dot is the first derivative with respect to position or the velocity. And X double dot is the acceleration. So from now on until all the field theory, if you do research with me, this is the notation you're going to use. That's what physicists do. We use dots because it's much easier. And with respect to time, these are time derivatives. Okay, so why is F equals ma a differential equation? Well, let me rewrite it in our physicist notation. F equals mx double dot. It's because this is a second derivative, okay? This is a second derivative. Therefore, this is a second order differential equation. If this was velocity, it would be a first order differential equation. And all this means is I can solve this equation and go backwards to get more information about my system. That's why this is a differential equation, right? Because this x double dot contains more information. It contains velocities and positions. And it's second order because I'm two derivatives removed from the position. Okay? Now, obviously, you can use some techniques. You can integrate this thing and get velocities. You can integrate it again and get positions. You can go the other way. And you've done all this in AP Physics C or whatever. You've integrated this thing many times, right? You might have a lot of complicated terms here, depending on your free body diagrams, right? You might have some forces going this way, that way, all over the place. So this is a differential equation. So I just wanted to bring that up because people talk about differential equations as if there's some complicated thing. It's really just another term to describe a certain class of equations. Now the Schrödinger equation is going to be what we call a partial differential equation. It's a differential equation with partial derivatives because it has multiple variables that it's dependent on. Here I only have a dependence on x, right? In the Schrödinger equation, I'm going to have a time dependence and a position dependence. That's why it's partial, because now I have to separate my variables. The derivatives are going to hit different variables, okay? And we're going to use the physicist's favorite technique, which you should all know, the physicist's favorite technique. Austin's here, so Austin will know. Austin, isn't the physicist's favorite technique separation of variables to attack a differential equation?
That's correct.
That's correct, exactly. So everyone must know separation of variables. Very, very important technique. Okay, so let's jump right in. Let's derive the Schrödinger equation. So this is the moment of truth we've all been waiting for. What is the F equals ma of quantum mechanics? What governs the system? Okay, and now we know about wave functions and probabilities and distributions and state vectors. We know all that stuff, so I don't have to go over any of it. So let's think about this. So for a free particle, E equals P squared over 2M. This is just a relationship from just normal, sorry, let me just be a little more clean today. E equals p squared over 2m. Now, automatically in quantum mechanics, we know that these dynamical variables, energy and position, momentum, are going to be promoted to 1. And by the way, today is going to be more of an interactive class because it's not going to be as abstract, and I think we can solve some problems together. So energy and momentum are going to be promoted to operators, right? That's quantum mechanics. So we know p hat. So p hat equals h bar over I d dx. This is in one dimension right now, right? I have no nabla, no gradient. And what's E hat? I haven't shown you E hat. E hat equals I h bar d dt. So it's a time derivative. Now, how did I get this? Remember a plane wave. I can write, okay, first of all, what is E? E equals h bar omega. That's just de Broglie wave relations, right? Which we discussed. Now, if I have a plane wave, that's equal to what? It's e to the I omega t, right? If I have some plane wave propagating. So if I apply this operator onto a plane wave, e to the I omega t, I get h bar omega. That's why this is the energy operator. Does that make sense? Because when it's applied to a plane wave that has some time dependence, I just get back some h bar omega, some multiple of energy. Okay, that's why that's the energy operator. Okay, so now let's write down this relationship using operators. So this becomes E hat equals P hat squared over 2m, right? And what does this become? This becomes I h bar d dt. And let's just say it's on some function, some arbitrary function f they're operating on. Put that here, right? Equals, and now p hat squared is minus h bar squared over 2m d2 dx squared on some f. Okay? Okay, now we're going to act this on the wave function. So now I just have I h bar d psi dt equals minus h bar squared over 2m d2 psi dx squared, and we have our Schrödinger equation. Okay, so there's our Schrödinger equation. And my favorite way to write the Schrödinger equation is just to write this. E hat on psi equals h hat on psi. So what do I mean by that? What is h hat? So E hat is just my normal E operator. And h hat is the Hamiltonian operator. So let me tell you what the Hamiltonian is. Okay, and obviously it's on the state side. Okay, so that's what I've compressed this equation into. So in classical mechanics, the Hamiltonian is a function. So in CM, the Hamiltonian equals kinetic energy plus potential energy. Or in physics notation, it equals T plus U. Okay? Don't ask me why we use T and U. We just do as functional get U. Okay, so here I've given, okay, so this is E hat, right? E hat on psi. Now this term, let's think about this. So what is my Hamiltonian? What is H hat? So now the Hamiltonian becomes an operator. So this is the Hamiltonian operator because we're in quantum mechanics, right? And what is the Hamiltonian? So the Hamiltonian in classical mechanics is equal to the total energy of the system. We have the total energy of the system on the left-hand side. It's equal to a Hamiltonian, except this is an operator. Now in quantum mechanics, the Hamiltonian operator is minus h bar squared over 2m, d2 psi, dx squared, plus some potential, v of psi. So I have a potential, right? So this is my kinetic term. This is my potential term. Okay? So basically, basically, the Schrödinger equation is really solving a Hamiltonian. That's another way to put it, right? And the Hamiltonian is extremely important because in quantum mechanics, in quantum field theory, you'll see that we can get all the dynamics from a Lagrangian, which is basically just a reformulation of this Hamiltonian. Okay? So all of the physics can come from the Hamiltonian. And you can see that we really can't do anything with this sort of equation without specifying the potential, right? Now we need some potential. Of course, we can't solve this equation. We really don't know what to do with this thing. Okay? Any questions so far? Please ask. Please feel free to shout out. I like when people ask questions. I don't like sort of just writing equations on the board. Okay, that's fine. Okay, so I'm going to rewrite it at the top. And this is an extremely important concept because, and I'll show you in a second how this is going to manifest in field theory really quickly. Okay, so let's write our Schrödinger equation. We have E hat psi on psi equals H hat on psi. And in its complete form, this is equal to I H bar del del t, del psi del t actually, is equal to minus H bar squared over 2m, right? d2 psi dx squared plus some potential d psi. This potential is what's going to tell us what to do. This is what's unique. Now in field theory, you're going to get a Lagrangian, which we're going to do Lagrangian mechanics. You don't have to write this down. I'm just showing this to you. The Lagrangian is equal to t minus u, kinetic minus potential. And you're going to get something that looks like this. 1/2, some weird term here, blah, blah, blah. Blah, blah, blah. You know, this looks really weird. We'll see what this is. But this is still a kinetic term. It's the analog of this. And we need a potential to get the dynamics. Very similar. That's why you need to know quantum mechanics before you do field theory. Now, if you don't know what all of this nonsense is, you'll learn this in due course. You need to know relativity and some other things. But this is the analog. And in field theory, we call this term, the potential that describes the dynamics, the interaction. Okay, so in field theory, the dynamics is specified by the potential again, but it's actually going to tell us about interactions. Okay, so I'm just showing you sort of the analog and sort of where we're going. Okay, that's not too important. Okay, so now we have our Schrödinger equation, but we have a huge problem.
Okay, so I have a short question, really. So here you rewrite, like you wrote this as energy operated multiplied by cat and Hamiltonian operator multiplied by cat, but in like another form. What is cat, or we just omitted here?
What is the, did you ask what is the cat?
Like, yeah, in the second equation.
Yeah, it could be, no, that's a good question. It could be any state. It could be any wave function, right? So we've looked at sort of Gaussian wave functions. It could be any kind of wave function, right? So like I said, how did I get this E operator? So if you have psi equal to just EI omega t, just some plain wave, now operate E hat on this, you're going to get back H bar omega, which is the energy. And see what you get when you add this on, you know, just make up, I would make up some random states, obviously complex. And, you know, we've described all of the characteristics of the wave function, right? It's complex, it's sort of Gaussian, it's sort of, so we know what these kinds of states could be, but what exactly the state is, that we haven't specified yet. Could be a variety of things, which is what we're going to spend time talking about. That's a good question, yeah. Okay. Great. Okay, so you guys probably saw something really funny in your last problem set, which is why I give you these problems, because it builds really nicely into what we're going to do. I know Rika was there. So Rika, what happened when you calculated the expectation value of momentum in the last problem set? Maybe she's not there. Did anyone calculate that? Does anyone know what they got? What you get? Okay, the answer is you get 0. Okay. No, sorry, that's not even really the point. Sorry. When you did the whole calculation for expectation value, you found out something very interesting. By the way, this was a very long calculation, but you find out that the time drops out. Okay, you find out that there's no time dependence at all in your calculation. So in other words, calculating the expectation value for psi gets rid of the time dependence. Those of you that were there, does that make sense? Was that something you went over? Okay. So we can employ a very nice trick here. So this is a partial differential equation. It has 2 dependencies, t and x. And what we can do here now to get the time independent Schrödinger equation, which will be easier to solve, is we can employ separation of variables. Okay, so psi right now is really a function of x and t, right? Psi is really a function of x and t. So I should really rewrite this as I h bar d psi of x and t dt Okay, and now what I'm going to do is I'm going to separate the variables. I'm going to have only position dependence for psi, and I'm going to create some arbitrary function with time dependence. And we're going to create a new time independent Schrödinger equation. So let's do that now. So I'm now going to separate psi of x and t is going to go to psi of x. And then I'm going to introduce some new time dependent function, f of t. So now let's rewrite all of this. So now my first term, I h bar d psi dt, is going to go to what? Well, psi has no time dependence, f does. So it's I h bar df dt, right? Psi equals, well, let me just rewrite what this term goes to. Minus h bar squared over 2m d2 psi dx squared is going to go to what? Well, x has the time dependence, so the position dependence, now I just have to write that f is also going to be this term. Okay, and v is now going to depend on psi and f, both functions, or the potential, right? Because now I have 2 functions that have dependencies. So now my Schrödinger equation becomes I h bar d psi, df. Oh, by the way, these partial derivatives, I'm sorry, I need to rewrite this because that's the whole point. These partial derivatives now become ordinary derivatives, right? Because now these functions only have one dependence. So that's what separation of variables does. What separation of variables does is it turns your partial differential equation into 2 ordinary ones. That's what makes it much easier to solve. So that's why I want to hammer in that point. Those should be ordinary derivatives. And I get I h bar df dt psi equals minus h bar squared over 2m d2 psi dx squared plus d psi f. Okay, I'm silly with my notation. Okay, I'm going to divide through by psi f. So I'm going to divide through by psi f, and I get I h bar df dt 1 over f equals minus h bar squared over 2m d2 psi dx squared 1 over psi plus v. Okay. Okay, so that was just a quick algebraic step. Now I can write down some new solvable separable equations. Well, I've already done the separation. So I have that I h bar, where is it, df dt, 1 over f equals E. Right, and I can write this as df dt equals, let me just, yeah, minus IE over H bar F. Okay, so that's my first derived equation. This isn't the time-independent Schrödinger equation yet, because I have no psi here. This is just some arbitrary function. And let's do some massaging to my other term. So I had minus h bar squared over 2m. Let me know if I'm going a little too fast today, because today's going to be a little fast. E2 psi dx squared plus, okay, I just remultiplied by psi, okay, here, equals E. I just remultiplied by psi, okay, so the 1 over psi drops, and then this picks up another psi. Oh yeah, and then this should pick up a psi, sorry, if I multiplied by psi. Okay, and now we have our time-independent Schrödinger equation. So this is it. This is the time-independent Schrödinger equation. Oh, I'm going to rewrite this neater. This equation is not as important, which you'll see for obvious reasons. But let me rewrite it, because this is what we're going to solve. Minus h bar squared over 2m d2 psi dx squared plus v psi equals e psi. And there we go. We have our time-independent Schrödinger equation. Okay, any questions on that procedure? This is sort of what you'll be doing a lot of. If you guys become physics majors, you'll be doing a lot of this procedure, because it's a useful tool in solving differential equations. Austin, what do you think? He's probably the separation of variables master by now, because in atmospheric science, you use a lot of these kinds of equations. Wouldn't it be E hat? Yeah, I'm very, I don't know when you, yeah, try to just ask them over audio so I can hear you if I missed it. But I don't know, I'm very loose with my E's, with my hats. Everyone kind of makes fun of me for that now, because I don't really care about the hats too much. But yeah, technically. Okay. Austin, I don't know if you were going to say something. I probably cut you off, but go ahead if you were. Okay, so such an equation has a solution, okay? And for differential equations, we can write down solutions that we call general solutions, okay? These are just solutions that are going to work. And when I write them down, you should check that they do work and solve the equation. Okay, so the general solution for this kind of differential equation is psi of x equals e to the minus I e t over h bar. Okay, so these are the kinds of solutions we get. General, obviously they can be edited. This is the most general solution one can get. And we know that psi on its own depends on x and t, but again, if I take the probability, which is what you found out, when you take the expectation value, you're basically doing this thing. This is just psi star psi, which is just psi star e to the I t e over h bar. Just mix them up, doesn't matter. Psi e to the minus I e t over h bar. You get that psi just has position dependence. Now the probability amplitude has time dependence. Okay, which is what you figured out on the homework. Okay, so the general solution now is a linear combination. It's a linear combination of separable solutions. So what do I mean by that? I might have a set of psi's, which are solutions. Psi 2 of x, psi 3 of x, dot, dot, dot. And corresponding to those set of solutions, I'm going to have a set of energy values, for example. Okay, so these are my eigenfunctions. So corresponding to the set of eigenfunctions, I will have corresponding eigenvalues, which is, we've already familiarized ourselves with that. Okay, so for example, if I have a psi 1 of x and t, some state psi 1, that's just equal to psi 1 of x, right? E to the minus I, E sub n t over h bar. Similarly, if I had a psi 2 of x and t, I'm writing the time dependence just as a formality. But you can see on the right-hand side, I dropped this should be a 1. I don't know why I wrote an n. E to the minus I, E2, t over h bar, and so on and so forth. Okay, nothing really fancy here. It's just using the general solution. Okay, and now this general solution can be altered and changed in a lot of different ways. And this makes sense, right? It's some exponential, it's a Gaussian, it's complex, it has all of the features of the wave functions. It's not really anything confusing. Austin, looks good to me. Okay, good. You're going to be my differential equation checker today, Austin. Okay, great. So let's write this really generally. And this is a big, I mean, this is, what I'm about to show you is kind of cool, actually. So psi of x and t in the most general form can be written as a sum, right? From n equals 1 to infinity of some coefficient Cn times psi n of x times e to the minus I e sub n t over h bar. Okay. Now this is a very, very awesome form mathematically. For those of you that don't recognize it, it's okay. This is just a Fourier series or a Fourier expansion. So you should look up what that is. I can explain it briefly. But a Fourier series is just a series of it's just a series of these exponential functions by increasing multiples, increasing integer values. And obviously, what's very suggestive about this is I can rewrite these exponentials as sines and cosines. So what a Fourier series tells you is any function can be written as a sum or a series of sines and cosines. Any function. And the Fourier series gives you the approximation of any function as a series of sines and cosines. So basically what we're saying is our wave function is nothing else but a Fourier series with different expansion coefficients, these CNs, which is what we're going to need to calculate. And that each mode of the Fourier series, each mode, what do I mean by each mode? As each integer value goes up, each mode, you're going to go up in energy level, okay? You're gonna go up in energy level. go up a dynamical level with each increasing mode in the Fourier series. So this has a very nice mathematical package, very nice and self-contained. Okay, any questions before we go to our first problem, the infinite square ball or particle in a box? Okay, great. Okay, let's go to the infinite square ball. So let's specify our first potential. I'm going to erase this so we can start from scratch with our first problem. But that's pretty neat and very, very useful. And we kind of saw this already because to go from momentum space to position space, we were doing a Fourier transform. So we can already see that the Fourier series is built in to the sort of machinery of quantum mechanics. Okay, so let's think about it. So I'm going to specify this potential. We'll call this the particle in the box or the infinite square ball, whatever you want to call it. And I'm going to specify a potential, V of x, right? That's going to equal 0 at some specified point. How do I want to label this? Yeah. And it's going to be infinity everywhere else. What do I mean by that? I'm going to show you. So let's draw this out. I have some potential. Some position. I have a point A, and there's a wall at A. And the particle is trapped in between these two sides. So my potential is 0, right? From 0 to A, right? What does that mean? There's no potential, there's no force there. The particle is free. It's sort of just moving around wherever in between the walls. And outside of this wall, the potential is infinity. The force is infinity. So the particle can't break the wall, right? The particle can't move outside of this box. The way I like to think about it is, let's say you have like a frictionless air hockey table with two walls and you just let the puck jiggle and it would jiggle in between in all sorts of ways, in all sorts of directions. It's essentially free. It's a free particle, except for this wall, this barrier. So it's confined because the potential has too much force on the sides. Okay, so that's the situation. This is a totally made up situation, but it's very instructive. And that's why people do it in quantum mechanics classes, because it teaches you a lot. Okay, so we know that inside the well, we'll call this a well, or inside the box, psi of, inside the well, V equals 0, right? So V equals 0 inside, so there's no potential. Outside the well, psi of x equals 0, right? So there's no psi anywhere outside of the well. Right, and we can write down our Schrödinger equation as this, minus h bar squared over 2m d2 psi dx squared equals e psi for outside the well. Or, yeah, no, inside the well. We want to talk about the particle inside the box, right? So we have no potential. I'm going to write this in a very suggestive way now. Okay, I'm going to rewrite this, and this I'll make this clear why I did it this way, as d2 psi dx squared equals minus k squared psi, where k is equal to 2me root over h bar. Why did I do this? This is an extremely, so now we have our time independent Schrödinger equation. It has a zero potential, okay? So this should be okay to solve, right? There's no potential for the particle in the box. So you might say, oh, Kyle, this is just a free particle. What's so weird about this? Well, we have some condition on it that we need to take care of. It's not just moving in all of space. Well, we'll get to that. We're not there yet. So far, it's just a free particle. I've written it in this weird way and defined this constant. Why? In classical mechanics, so this is another second order differential equation. This is exactly like the harmonic oscillator. And do you guys all know what a harmonic oscillator is? Okay, I'll explain it. Basically, you need to know what a harmonic oscillator is. Everything, I'm not even really over exaggerating when I say everything in physics is harmonic oscillators. In fact, field theory is just an infinite amount of harmonic oscillators. So you better know what it is. So what it is in principle is I have a wall, I have a spring attached to the wall, and I have some weight attached to that spring. Okay, and I'll draw it out. So I have some wall, I have some spring, right? And I have some box attached with some mass, okay? And if I pull that box out and let it go, this is gonna oscillate, okay? And what are the solutions to the oscillator? It's just sines and cosines. It's just oscillations, okay? So you can see why this makes sense because we're gonna be dealing with sines and cosines and sort of wave-like things. But let me show you how this is the direct analog of the classical system. So this is simple harmonic oscillator. And if you're not familiar, you should look in Taylor. You should do this before we do field theory. Classical mechanics, chapter 5. Okay, there's a PDF online. Very nice chapter. But here's what I'll say. Here, let's show how this is the direct analog. Okay. So let's just start with F equals MA. X double dot. Okay. Okay. I'm gonna write this neater. I need to be a little neater with my. Okay, F equals MX double dot. Now if we have a harmonic oscillator, the forces are just the spring forces, Kx. Does that make sense to everyone who've taken high school physics? So this would just be MX double dot equals minus Kx, because that spring force is pulling the box back, right? So the vector is pointing this way. Okay, so now let me bring this over. I get Mx, well, let me just leave this here, equals minus Kx. Sorry, I don't know why I rewrote that. Okay, we know that omega, the frequency in classical mechanics, or omega naught we'll call it, the natural frequency, is equal to the square root of K over M. Right? This is what we learned in high school. So if I divide through by M, I get X double dot equals minus K over MX. This is what? Omega naught squared, right? So this is just X double dot equals minus omega naught squared X. Yeah? What's X double dot? It's just the second derivative. So this is really just written as D2X, sorry, just D2 dx squared equals minus omega naught squared X. Looks really similar to this, right? Practically identical. So this is just the second derivative. I have a function here psi. We can put a function here f, whatever. This is a frequency. This is going to mimic a frequency, which makes sense, right? Because what did I put here? I made k some function of e. And we know that e is going to take on integer values, right? So this mimics a frequency, sort of a quantum frequency, a discrete frequency with n equals 1, n equals 2, n equals 3, so on and so forth. And then it's squared, and I have my function again. So it's very, very closely related. That's why it's very helpful to get the classical analogs, because it's coming straight from it. I hope that's cool. I think it's pretty cool. So all this talk for the quantum world is so different than the classical world. They're still closely connected, okay? Okay, let's go back to our, that was just a digression, but it's an important one. Okay. And if that's fuzzy, come speak to me, it's fine. I'm not expecting everyone to have seen it. By the way, if you take classical mechanics, I'll give the plug again, you'll spend probably 2 weeks solving that equation and solving all the intricacies and using all these techniques. Okay. Okay, so I've written it in this form because now I get some really nice general solutions. I get oscillations as my general solutions. So I get that psi of x, and you should check, right? Just plug this in and crank it out and check that this works. Equals a sine. Do I want a sine or a cosine? I want a sine. A sine kx plus b cosine kx, which you probably recognize from high school physics, right? As solutions to the harmonic oscillator. They probably didn't tell you how they got them. Maybe they did, I don't know. Okay, and A and B are the key. A and B are what we need to calculate, okay? A and B are fixed, so these are called boundary conditions. And very, very important in physics to know your boundary conditions. So these are fixed by the boundary conditions. So what is really the only boundary condition we need to take care of? This. This is a boundary condition. Okay, so we know that psi of A equals 0 outside the well. Okay, so now I can just rewrite these boundary conditions as psi of A equals A sine 0 plus B cosine 0. Just plugging in the boundary condition. This term will drop because it's sine 0. This term will be 1. So I get a B. Psi of A equals 0, therefore my first boundary condition, B equals 0. Okay, that's done. So now let's talk about this piece now. So we've solved for this boundary condition, and we know that because of this point, this doesn't even contribute. This oscillation does not contribute, okay, into the solutions, into the energies. This oscillation will. This part will. So how will it contribute? Let's think about it. This is where the art kind of comes in of solving these things. Okay. Questions before we continue? And you could play around with all kinds of boundary conditions. Maybe you have a finite square well. Maybe you put like a roof on it. Maybe you put a boundary this way, a boundary down, a negative boundary. Okay. Okay, let's look at the A sine kx part. Or we're going to call it A sine ka. Right? Because now we're dependent on A, not x. So basically, we can have Ka be any multiple of pi. Right? And that's going to give us some value. It can be any increasing multiple of pi. Would it be, it should be plus or minus. Let me think though. No, that's right. Okay, so now we have a set of values, right? And now I can rewrite this expression in the following way. And you should work out this algebra to get, I mean, it's not very complicated, but whatever. I can get that Kn right? So now all these multiples is equal to what? N pi over A. Where N is just a series of integers. And A is the boundary condition. Maybe I move the boundary condition somewhere else, right? Maybe I shove it here. Maybe I shove it here. Maybe I shove it here. And the reason this is non-zero is because I've already gotten the zero contribution from outside the well. You could easily see how I could just do this the other way. Make the A contribution 0 just by changing the values. It's not very difficult because cosine and sine are periodic. Okay, and now we're almost there. Because now we can repackage this as a series of energies because we know what K is. I've defined K in a very particular way. Remember, K is equal to is equal to a function of these energy values, right? That's why this is so important. This K and this K are intimately connected. And take a second to piece that together because that's super important. Before I write down. Can I write down? Can I erase this board? Okay. Okay, so let me write down what E equals to then. Now we have all the tools to piece it together. We've taken into account the boundary conditions. Now let's write down E. Okay, En. Let me just think about the algebra in my head. Wait. R squared Kn squared over 2m. You correct me if I'm wrong. N squared pi squared over ma squared. Am I missing something? Yeah. H bar squared. Okay. So now we have a bunch of energy values. And this is really weird because now we can't just have any value for energy. That's what's so cool about this now. This is crucial. We cannot have any value for energy in a quantum system. Deriving this equation for the energy, right? Using just basic oscillation. The only tricky part here was the fact that we had a boundary condition. I hope that's clear. I mean, other than that, these are very nice general expressions. Anyone have an idea of why I'm saying that? Like, why am I saying that we can't have a continuous stream of energies? That's what's super important. And while you think about that, I'm going to write down the function for psi inside the well. So inside the well, psi n of x, any multiple of psi. So now Olha was asking me, what is psi? Now we figured out psi in this situation. It's equal to 2 over a root. This is the normalization. I could prove it to you tomorrow if you want. It's really trivial. That's why I don't keep showing you those integrals. This is just to make your life easy. You just say, oh, great, they gave me a normalization. Beautiful. I don't have to come up with it myself. Sine, right? N pi over ax. Okay, so that's my general wave function with multiples of n. Why are they sines and not cosines? That's just the way I chose to do it. You could have came up with some cosine term. If you rejiggered the boundary conditions or done, could have come up with anything. Okay, can someone just tell me why this is telling me now? I can't have a continuous stream of energies.
Just h bar squared.
Sorry?
Just h bar squared.
Well, that has something, that's just a constant, right?
Okay.
So I could still have continuous energies.
So just n are integers.
Exactly, n are a series of whole number integers, precisely. Right, so n is not a continuous stream of numbers. That's why. And that's super important because it's telling me energies can only be certain values and discrete values. and they're set whole number values. That's kind of a big deal, okay? Because it changes the game in terms of how we're going to observe things. Okay, so let's draw out the first 3 states of this, of the infinite square well, okay? So the first state, so psi 1 of x, okay, just using this. So here's A, right? Here's my boundary. Now how does psi look inside the well? Looks like this, okay, if you graphed it out. Psi 2 of x, so now we're actually seeing this physically. Now we're actually drawing this out physically. Okay, that's psi 2 of x. And you should be noticing some very interesting things, which is what I'm going to ask you. Here's psi 3 of x. Okay, so it's 10:29. Let's come back at 10:35, and I want people to give me some ideas on some patterns they see, or some trends they see. So before though, this is called the ground state. This is the first excited state. Or first energy state. So now these are like, so now we can see, now if we have the hydrogen atom, we're going to get all the energy states and all the quantum numbers. So now in chemistry, they just say, oh, here are the energy numbers for the hydrogen. Right, they come in these values. Well, no, now we're going to derive them. So now we're getting the machinery. And this is the second excited state. There you go, guys. You're computing things now. You can see them, but we should see some trends. So I'll be back at 10:35. Take a 5-minute stretch break, look at them, meditate upon the wave functions. And if you have questions, feel free. Man, we have a lot to get through today. I'm probably going to run late today. Okay. Okay. Oh, no, everyone has 2 minutes. I shouldn't take away.
I had a quick question. I might have just written this wrong, but earlier, did you say that psi of A equals 0 inside the well or outside?
Outside.
Okay.
That'd be bad if it were inside the well. Okay.
And are there any research topics related to this that we could do?
I don't know. Maybe you could come up with your own wells.
Okay.
I think this is where it's getting a little less abstract. So I feel like people are getting a better handle on this. Is that a good assumption? Okay. I see shaking cats. That's why I said, don't worry, guys. Last week is the last week of really abstract. See, that's the way it is. But now look, all the machinery we developed is helping a lot, right? Now imagine I just threw this at you. Yeah, okay, you'd get what's going on, but you wouldn't really understand where it's all coming from. What are all the pieces? Now we know all the pieces. Now it's just putting it together. So now we can start, actually solving some systems. And then it will get very quickly abstract again when we do the path integral. Then it's going to get really abstract again. So that's okay. That's what happens. We need the path integral for field theory. Although I don't use it too much myself. And I might spend it, because we actually have a lot of time. When I was planning the schedule, I didn't realize how much time we had. I might spend a class just on symmetry. Just because I really want to focus on symmetries. Just because I think it's important. Okay, so let's talk about it. Okay, folks. So what are the patterns you see? Let's get some of these. Mansoor, we haven't heard from you. What can you tell us about these states? And maybe it's too early from break. They didn't get back on time. It's okay, I'll call on him in a bit. Austin, what do you think about the states, if you're there? I have to guess if people are on camera or not. That's okay. We'll give people a few minutes then. That means not everyone's here yet. So. Also, for those of you in this group chat, whoever put your email there, I'll connect all of you guys. I'm writing a pop science piece for the New Yorker, actually. And I will send it to you guys. I'd like your thoughts. And it has to do with some of the ideas we've been talking about. So you can tell me if it's clear or not. Or there's only one equation, don't worry. This actually sprung out from an idea I had with Bob, actually chatting, on a Sunday. I came up with this idea and I was like, let me write this into a piece, and it seemed to have worked out. So I will send that to you guys. Okay, let's continue now. We're running out of time, so. Anyone have any ideas? Any patterns that they see? We'll call on Mansoor again. Maybe he's back or she's back. I don't know.
Wave function stays the same length depending on the excited state, but the shape changes. Right, the shape does change, but what can we say about how it's changing? What's going on here? So the first thing, I'll say the first thing. How about that? The first thing is, with each increasing excitation, I get an extra node. So in other words, it passes through the x-axis one extra time. So here it passes through once, so I have one node. Here I get two nodes. Here I get three nodes. Also, these are different modes of the Fourier series, right? So as you change the mode of the Fourier series, the mode being n, this is another Fourier series again, you get different excitations. Can someone tell me about the evenness and oddness? That's what I really want to get at. That's what's more exciting. So, Olha, is this function even or odd? Is psi1 even or odd?
So it's, I'm sorry, I don't remember like the translation of even or
Okay.
odd, so I can just mess up.
Okay, so let's do that now. So an odd function is a function that's asymmetric or symmetric about the origin. In other words, the way I like to think about it is it's a function, if you integrate it, you get 0 because they're exactly opposite on both sides of the axis. So this function, if I integrate it, I'm not going to get 0. I'm going to get a non-zero number. So this would be what? This would just be even, right? Because, I mean, if I integrate this, you'll see this more clearly in a second. What about psi 2? Jenna, what do you think about psi 2?
It's odd.
It's odd, exactly. So now do you see that better, Olha? How this is odd? It's completely opposite. If I integrate this, I'm going to get 0. Okay, good. Okay, now let's see the pattern. What about psi 3? Who's this? REM. What about psi 3? I don't know if they're there. Austin, what about psi 3? Okay. The wave number seems to be increasing. Yes, yes, and this is even. Yeah. So we're going to go even, odd, even, odd, even, odd. Okay, we have the pattern. What's very interesting is this is not going to contribute. Sorry, my mute button. That's okay. This is not even going to contribute to your expectation values. So that's why that's important, right? That only the only the odd numbered states are going to contribute. So now you have some more idea about how this whole apparatus is going to fill out. So in this system, the even numbered states are going to have no contribution, right? Because they vanish in the Fourier series. Now, if I did this in terms of cosines, I'd probably get the opposite. Although I don't know, because your ground states are ground state. So you figure that out if you want. Might be a fun research project. Okay, let's prove some more. Let's prove some more of the qualities that we have described so many times in this class. So they are also mutually orthogonal, right? So psi m star of x, psi n of x, minus infinity to infinity is just delta m n, right? They're orthogonal, which we've described many times. Now, do you want me to prove this to you? The integral's really nasty. We can prove it for the infinite square well. Does anyone want to see that long integral? Or can you spare me from doing it? You want to see it? Okay, okay. Let's do it. All right, let me think about it though before I jump in. No, you should see it. You should see it. So let's see it. Let's do it. Okay. So let's do this for the infinite square well. So for the well. What is this going to be? I'm going to get a 2 over a for my root 2 over a times 2. I'm going to have two wave functions. We're going to integrate from 0 to a. We're going to have a sine m pi over ax times a sine m pi over ax. Why did I write it this way? Okay, now we just do this long computation. Let me think about how I want to do this. You guys should compute it as well on your own as I go through this. Okay. This is usually how I attack these. Okay, that gives me that first term. Okay, I just rewrote this in a unique form, which is what I always do. My way of integrating is really weird. So you should put this into like SimLab and see how it does it. I do integrals really, really weird, just from trial and error. Let me just think. Yeah, you have to make sure I'm doing this right. We'll get through this. I just have to make sure I'm doing this okay. Oh yeah, okay. Wait, but let me just think about that sign in between. Yeah. Okay, it's not that bad. Okay, fine. Okay, from 0 to A. Okay. Now we need to evaluate. All I asked for it. It's not my fault this time. Okay, now let's evaluate this. Sine m minus n I over m minus n 1 over pi. Do I want that in the same thing? No. Okay, yeah, okay, I got it. Okay, that's what the final expression you end up with. And this is just equal to 0. Okay? If they're not the same. Yeah. Okay, and again, just for clarity, and I'm sure there's a better way to do it. I just like rejiggering things with sines and cosines a lot. That's just how I do these faster, but if you find a better way, stick to it. And again, we just derive that psi m star. Okay. Olha, was that okay? Cleared up? Okay. You asked for it. Well, you know, it's only fair. I've been making you do all these long integrals, and you've never done one here. So you put me on the spot, which is good, Okay, and obviously all our states are complete. So I'm just gonna write this generally, that all our states are complete. This is from n equals 1 to infinity. Cn psi n of x, which now in our context is just 2 over a root sum from n equals 1 to infinity.
Right.
Cn sine n pi over ax. Okay, so that's the completeness theorem. Okay, where now I just have a sum over all my states from the square well. Any question? Okay, I'm going to skip the free particle and show you some more important expressions. Free particle is nothing. It's basically what we did without the boundary conditions. So it's not a big deal. What do I mean by free, by the way? A free particle just means sort of moving in space and time. Nothing's bothering it, nothing's acting on it, no force is acting on it, right? So there's no potential, okay? Or no interaction. We can even call it an interaction, because that's what we're going to call it in field theory. That's all I mean by free. Again, this is just the Fourier series, right? For f of x, just a Fourier series. You should look up, Wikipedia has a really nice animation on Fourier series. Very helpful. Okay, so now let's just write an expression on how to compute these expansion coefficients. Okay, so let's just write an expression on how to compute expansion coefficients. Okay, so we have this theorem, right? So Dirichlet's theorem. So Dirichlet's theorem tells us that the expansion coefficients can be computed like this, which is kind of intuitive. I should have a psi of x here too. I just missed that. Okay, so I just get this expression. Well, okay, I mean, psi of x is just some any function f of x. I'm being very loose, it doesn't matter. Okay, so therefore, Cn equals the integral psi star m of x, any arbitrary function f of x. This can also be a wave function, it doesn't really matter. Right, and for the infinite square well, I'm going to write this in the more explicit form. Psi of x and t equals over 2a root sine n pi over ax e to the minus I n squared pi squared h bar squared over, and I'm going to continue the exponential here, 2ma squared. This should actually just mean h, I think. Yeah. Two ma squared. What am I gonna put over there? 2ma squared Should be a T somewhere in there. T. I'm pretty sure that, no, that's right, that's right. Okay, so now I've just input our expression for energy that we derive. Nothing crazy. Okay? Any questions before we look at the 3D Schrödinger equation, which is straightforward? So we didn't do the free particle. We don't have time, it's okay. And we didn't do the velocities, which is fine. I'll do that next time before we do the harmonic oscillator. Okay, let me write down the 3D Schrödinger equation. So the 3D Schrödinger equation is really simple, except now our h bar over I ddx is just going to become a gradient, right? In 3 directions. So now the 3D Schrödinger, not just time independent, just I h bar beside ut, and this is what I'm going to start using from now on. I'm not even going to really bother with the 1D nabla squared, right? Psi plus V psi. You guys know what nabla squared equals, right? Should I write it out? Okay, I can write it out. Nabla squared is defined as the gradient operator with second partial derivatives in each direction. So, oh, I should actually tell you the name for this so you know what it is. This is called the Laplacian. Okay, so we have a Laplacian. Okay, and it's just like the gradient, except instead of first derivatives, it's second derivatives, second partial derivatives. So we have a Laplacian. It's so funny how we use these random symbols. Triangles, we're going to use some boxes, squares. We'll even have to draw like a 4D cube as one of the symbols, or a hyperplane. I'm just kidding. We don't draw hyperplanes. That would be annoying. Okay, so what did we do? We finally solved for something. We got some energy eigenstates. We analyzed them. We figured out what this particle was doing. Although this situation is not very physical, I mean, in real life, it's a good starting point because to do the harmonic oscillator and to do the hydrogen atom, you're going to need more machinery. We're going to need special functions, special operators. For the harmonic oscillator, we're going to need creation and annihilation operators. Sounds very fancy. And for the hydrogen atom, we're going to need spherical harmonics and Legendre polynomials and Hermite polynomials and all these fancy names for very simple. You know, this is, I'll spend the last few minutes giving you a little rant. Austin has heard this so many times. Math is not too complicated. People make it sound very, very complicated, like no one can do it. Only like some crazed man in his room who is going insane can do math. It's not true. A lot of the math is really simple. Okay, so I really hope the math is not bothering you. If it is, come talk to me. I don't want the math to stop you because the physics should be bothering you. Okay, that's how you know if you're comfortable or not. If the physics is bothering you, 2 thumbs up. The physics should be bothering you because these are very complicated questions. They're very deep concepts. The math should not be bothering you, right? The fact that this is the 3D version, shouldn't be really, it should be trivial. Or the fact that this is the Fourier series and the modes are going to increase, the modes and the expansion are going to make this look a certain way. By the way, you should draw out all the modes. Like you should draw out n equals 4, psi 5, psi 6. And there's Gabe. So Gabe, we were talking about the particle in a box. You have any thoughts on that? Or the infinite square well?
See, it's pretty cool, I guess.
I told them it's like it's like your first real calculation, right? Where you actually get energy eigenstates.
Mm-hmm. Yeah, and it's like you can think of it as almost as a precursor to something like the hydrogen atom.
Exactly. See, me and Gabe, we're on the same wavelength. I said the same exact thing. So there you go. It's not just me. It's everyone says the same things because it's true. Okay, excellent. So I will look forward to your ideas for next week. Gabe, I don't know if you got to see the update, but there's no problem sets the next 2 weeks.
Mm-hmm.
So you're off. Yeah, so that's perfect timing for midterms, right?
Almost.
So wait, so are you in Belgorodov's class?
Yeah.
Do you like it or?
He's all right. He doesn't seem very understanding, I guess. He gave us like
he taught graduate GR, so maybe he's not used to like.
Yeah. I mean, he gave us like 4 or 5 days to do a very long problem set.
What? Wait, what are you covering?
Oh, we're covering a little bit of everything. We're doing, like, we just did like review vector analysis. Then we did curvilinear coordinates. And we're going to do like everything like PDEs all the way up to groups later too. So.
Oh, very nice. And then what about Rachel Rosen?
Oh, that's going all right too. We're just, what are we doing now?
Probably special relativity, right? 4 vectors.
We're just finishing special relativity. So.
Oh, nice. So you like that the second problem was those Lorentz matrices, right?
Yeah.
Because that's probably all you're doing, right? Boosts, rotations, all of that. Okay. All right, great. Okay, guys, take care. I'm going to set up your group chat right now. And then I'll pop in and out as usual. Okay? Nice work today. All right. Stop this recording.